Hello, everyone. We are Group 5, and our project is on the analysis of blood flow through clotted veins. The main reason we chose this topic is because propagation and severity of blood clots is a major health risk that stems from COVID-19. Blood clots are dangerous because they can interrupt blood flow and cause permanent damage to vessels and organs. We hope our analysis will help scientists and doctors gain a better understanding of how blood flows through a vessel and around the clot, so that they can properly diagnose and evaluate vascular disorders and long-term health risks. For our project, we had two main objectives. First, we wanted to understand the effects of a blood clot in a blood vessel under the forcing function of the pressurized flow of blood. Secondly, we wanted to understand the variations of age and existing condition on the blood clots and required volumetric flow to avoid long-term damage. In order to truly understand our analysis, we needed to know the fluid properties of blood. We found out that blood can behave as a Newtonian under certain conditions and has a density that roughly matches water. Since blood properties are often interdependent, its viscosity depends on shear rate and hematocrit, also known as red blood cell concentration. Its flow rate also depends on pressure. There are a couple of characteristics that help describe what blood vessels and blood clots are. Blood vessels are mostly elastin and highly distensible. As mentioned earlier, blood clots can obstruct blood flow. In addition, they are harder than the average vessels at an elastic modulus of 14 megapascals. So it's mainly fibrin. But blood clots can cause backflow, distended veins, and some really serious health problems. On the right is a physiological flow parameter chart that measures a blood vessel diameter versus its shear rate. To the left is three types of blood flow. So on the farthest, so the left, you have the normal blood flow, and then in the middle you have a deep vein thrombosis, and on the far right you have a clear picture of embolos, and a zoomed in picture on blood. And then for normal blood pressure, you want to be in between, or you want to be less than 120 millimeters of mercury, which is considered systolic. And you also want to be less than 80 milligrams of mercury, which is considered diastolic. And then elevated is in between the ranges of 120 and 129 millimeters of mercury, and diastolic is less than 80 millimeters of mercury. So just certain ranges you have to be aware of when considering and talking about blood pressure.
So we will be going over the theory of the ANSYS simulation, and it will revolve around three concepts. The first being the conservation of mass, which would be the mass flow inlet will equal the mass flow outlet. So the blood going into the vessel, the flow rate of that would equal the same as the blood going out of the vessel. This can be also derived into the continuity equation for fluids, which would be the partial derivative of the density with the summation also of the partial differential of the x, y, and z axis. And since we're going to have rho as a constant for it being blood, it can simplify, this governing equation can simplify to the partials of the x, y, and z axis, the summation of the partial of the x, y, and z axis equaling the 0. The next one would be the conservation of momentum, or the Navier-Stokes equations. The conservation of momentum being the summation of forces equaling mass times acceleration. That can be also derived into the x, y momentum, x, y, and z momentum in a fluid standpoint. The first, and we could use an example as the x momentum here. The left-hand side would be the acceleration terms. On the right-hand side would be the pressure gradient, and then the viscous terms, and then the gravity term. So using the boundary conditions from our ANSYS simulation and our parameters, it can help produce and simulate the outputs for our project. And finally, the energy balance or the Bernoulli's equation can be used when the initial pressure head, kinetic energy, and the potential energy would equal the summation of the pressure head, kinetic energy, and the potential energy along with the head loss. So the head loss would revolve around, would include the friction factor. And the friction factor is a function based off the Reynolds number. So the Reynolds number in a fluid standpoint is the ratio of inertia force and the viscous force. So for a laminar flow, and a laminar flow is the smooth uniform flow through path. It would be, the friction factor would equal 64 over the Reynolds number. As opposed to the turbulent flow, and the turbulent flow would be in irregular fluctuations and mixing of flow. The friction factor of that for a smooth pipe, assuming it's going for our blood vessel simulation, it would be 0.316 over the Reynolds number to the power of 1/4. So getting the friction factor based off the flow and putting it into our head loss, and then getting our head loss in, adding it into the Bernoulli's equation for our energy balance system. Next, we will be talking about the assumptions for our simulation. To begin with, with the blood, we were treating the blood as an Newtonian fluid. Approximately, the density would be about 1 gram per centimeter cubed. The viscosity would be 0.1 pascal seconds, and finally, the velocity would be 40 centimeters per second. And then next would be the blood vessel. The blood vessel we would treat it as 100% elastin and have a constant geometry. So throughout, so it would be a radius of about 5 millimeters, a length of 20 millimeters, a walk thickness of about 0.4 millimeters, and having a Young's modulus of 1 megapascal and a Poisson's ratio of 0.41. We will be having, so the inlet pressure would equal the outlet pressure of the blood vessel. So as the blood is going through the inlet and then reaching the blood clot and then coming out, we're treating those as equal pressure for each endpoint. And then along with the blood clot, we're treating the blood clot as 100% fibrin and having that in the center of the blood vessel, so center of the segment. And then with our project, we're going to have various simulations because we will be doing various blood clot sizes, and then having the Young's modulus of the blood clot equal 14.5 megapascals.
So here we'll talk about the FE model. So in the FE model, we've initially tried to do just a fluids model. However, it did not work out quite well, and that's because the walls were too rigid. So when the walls were too rigid, the pressures that we were seeing were ridiculously unrealistic, and that's because the walls were not there to absorb some of that pressure, or the walls were basically not given any. So therefore, we decided that we want to explore the transient structural coupled approach with fluid. The idea is that we will set up a fluid domain, and we will also set up the transient structural domain, and we'll do a very limited number of steps. And we're really interested in the final result, where we already have the vein deformed. So what kind of fluid are we? What kind of fluid interaction are we seeing? Or fluid results are we seeing? All right. So the original model setup was to just use the two bodies, the clot and the vein, and just being attached to each other via a bonded contact. And they were both assigned the respectively material properties. However, that approach was not very successful, and that's because the material properties of the vein were very, 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 it was a low modulus of elasticity, and because of that, we were running into a lot of divergence problems, especially also with the contact between the clot and the vein. So therefore, we've decided to do maybe a little more simpler approach, in which is model, instead of two bodies, we'll model them as one body. So kind of like a little bump, if you will. And we will check out the interaction there. And the material that we're going to assign to this solid is going to be kind of like a stiffer material. So it's kind of like a little bit on the blood clot level. And the main reason is we wanted the model to converge and not collapse on itself. The setup that we've done was the solids, they all got a linear tetrahedral elements. And we actually predetermined the element size of 5e to the negative 4 meters. And the idea was to actually keep it small, but not very small. This way we can actually compute that the different iterations it needs in a transient domain. The other thing was the fluid domain. So the fluid domain got two types of meshes. So the one was a little bit of a finer mesh because of the curved features. We want to understand a little bit the boundaries and what's happening in the boundary conditions. And there were tetrahedral elements as well. But for the fluid iterations, we set up a dynamic meshing that was basically reacting to the deforming wall. So every time the wall would deform, it would remesh the fluid to kind of represent that. Convergence. So before I talk about convergence, let me talk a little bit about the transient stepping and what we've done here. So in the transient stepping, we've modeled up to 1 second, and we've modeled at an increment of 0.01 second. And the idea was we weren't really interested in going very deep into the small details as things are developing. Like I mentioned before, we were really interested in the end game. So that being said, originally we ran into some convergence problems because of the elasticity due to pressure interactions on the walls. So things were just collapsing pretty easily from the structural side. Therefore, which actually matches what we are expecting from the theory, and we're going to talk about it a little bit later in the discussion. However, to make sure that we can run a successful simulation, we had to actually go out of our way and do an assumption that the wall is a little bit stiffer than what we took from initially. And then we ran 45 iterations, and it actually converged. Now, when it comes to results, we've seen 3 really major results, and they kind of match what we were expecting too. One is the pressure. So for the pressure, what we've seen is that the pressure was quite a bit large on the inlet side. So it actually increased by about 15 millimeter of mercury. However, after the inlet, or after the clot, there was a slight pressure increase, and then it went into pressure decrease. So it increased by about 5 millimeter of mercury, and then it started decreasing after that to 5 millimeter mercury, which makes sense again with what we were expecting. That's one. 2, the velocities. Obviously, we have a bottleneck situations here, so the expectation was that the velocity is going to be its fastest as the pressure is developing, and that pressure gradient is actually developing. That's one. And then last here is the eddy viscosity. So the eddy viscosity actually showed us quite a bit of interaction that the fluid is having with itself in terms of a fractional phenomena. And that actually makes sense with what we read through with the literature, especially with the risk of a backflow that typically happens due to blood clots. Now let's talk about the deformation of the walls. That's another phenomena that was actually very interesting. So one is, let's talk about inlet side. So one thing I don't think I discussed here earlier is that the boundary conditions of this vein was actually, it's bounded at the section wall of the inlet and outlet, as you can see here in the blue. So what was happening is, as the pressure built, right, we were seeing an expansion in the vein's wall right before the clot. And then you can see the red region at the bottom here, where it was showing us the area of maximum pressure on the wall. And that makes sense. And that's kind of like the area right in front of the blood clot opening. And then after that, you see a slight decrease, a slight increase also, or a slight expansion in the wall. And that's because of that pressure buildup right after the clot that we just discussed. So yeah, so that being said, if we were to go into the model here, we see exactly the phenomena that we're just describing in terms of the performance of the vein and how it collapses in some areas and then it actually expand in other areas. So you can see it's actually expanding right before the clot. And then it's creating this like pinched shape, if you will. So that's one. And then the other thing is the fluid interaction. So you can see these are the eddy viscosities and how it's kind of like built up in the wake region, if you will, after the clot. And that's what causes a lot of like fluid frictional interaction, and also raises the risk of a backflow.
Overall, the results of our fluid analysis do match up with the behavior of veins in real life with blood clots. Blood clots have been known to elevate blood pressure both around the clot and afterwards. And these low pressure areas that can occur before the blood clot tend to be areas where there's backflow of the blood. Now, blood clots do often cause permanent distension of the vessels as well. And while this does help to offset the pressure a little bit, this can in turn cause further backflow, further damage around the area of the distorted vessel, and further clotting down the line. As you can see in the picture on the right, backflow does also contribute to further blood clotting. Now, while our model was mostly accurate, there are some potential losses and inaccuracies in what we use. As Ituah mentioned earlier in the research, blood can behave as Newtonian in large enough vessels, but this is only true to a certain degree. After all, blood is not homogeneous. One potential contributor to this is what's known as the Farias-Lindquist effect, which mostly occurs for smaller vessels. The Farias-Lindquist effect, as seen on the right, shows that blood viscosity does tend to decrease with the radius of the vessel, but it suddenly increases once you reach a critical small radius. Now, while we're dealing with big vessels in our analysis, with a sufficiently large clot, you could end up seeing some resemblance of the Farias-Lindquist effect. And because we exaggerated the blood clot sizing, this could have kicked in with our analysis, but improperly been ignored. Another thing that we ignored was the non-homogeneity of blood vessels and blood clots. While it is correct that blood vessels are mostly elastin and blood clots are primarily fibrin, this does tend to vary for different blood clots and different vessels. Some vessels, for instance, will have higher amounts of collagen due to needing to hold more stiffness. And blood clots can also be formed by other materials, such as cholesterol deposits or even calcium deposits, which can happen with older folks as well. The sensibility can also vary by vessel since, as mentioned, the material properties of a blood vessel are not consistent throughout the human body. And blood clots often do not form with perfectly even geometry as we used in our model. This can cause blood clots to break off and go to different parts of the body. As we mentioned earlier, it is possible for arterial wall deposits of calcium or cholesterol to build up. These are health conditions which can lead to more blood clots and pose as a risk factor. Part of why it's important to study blood clots is because as you get older or develop other health conditions, you are at higher risk of blood clots or at higher risk of severe complications arising from blood clots. The older you get, the more likely you are to have hypertension or weakened veins due to various injuries throughout your life. And conditions such as varicose veins and hypertension, while not in and of themselves fatal, can lead to severe blood clotting. As a matter of fact, varicose veins in particular put you at a high risk of deep vein thrombosis, which is often fatal. In conclusion, blood clots will often result in elevated blood pressure even after blood passes the clot. And while some of this elevated blood pressure can be partially offset by distortion of the vessel, this will still cause health issues. Finally, due to high distensibility of the vessels, fluid analysis must be done in conjunction with structural analysis of the blood vessel itself. References are shown here.